So today, I'm hoping to finish topic two. So this is that we're talking about conservation of energy and energy transfer in this unit. I think we should be able to finish it today. And that being said, keep an eye out for the homework set associated with this unit probably later today. Okay, and then I'll give you at least a week to work on it, but I'll make sure it's not due at the same time as something else. Okay. All right, let's get back to where we were. Okay, so we were talking about different types of work and how we can use our conservation of energy equation to find boundary work. We looked at expansion or compression work, so this is moving boundary work. We also looked at constant pressure processes or isobaric work, as well as constant volume process, which of course has no work. All right. The next type of process we're going to talk about is a polytropic process. So during an actual expansion and compression process of gases, the pressure and volume are often related by an expression that looks like this. So we have pressure times volume raised to the nth power is equal to C, where N and C are constants. So this N refers to this exponent, and then this C is this constant here. And those constants are going to depend on the process. So what we're going to do in this kind of subsection of the notes is we are going to determine boundary work for a process that follows this kind of a rule relating pressure and volume. Okay. So for a polytropic process, where I'm going to rewrite this equation again. So PV to the N equals a constant, which that constant is C. The value of N can be positive or negative and depends on the type of the process. It's important to note that not all processes are polytropic. So this is a very special case. So you will have some indication to use a polytropic process if that's what I mean for you to do. Okay. So for example, if you had a relationship between pressure and volume that looks like this. So A and B are constants. If we have this form, then this is not polytropic. If our B constant is not equal to 0. So if B is 0, then this is polytropic. If it's not 0, then it's not polytropic. If it is polytropic, or if B is equal to 0, then this is polytropic. Because then our expression looks like P equals A V squared. And we can rewrite this as P divided by V squared equals A, which is just P times V to the minus 2 equals A. So we have that N is equal to minus 2 and C is equal to A. Okay. All right, so if we have a system where we have a cylinder and a piston, this is our piston cylinder system. And this is a gas in here. And in this gas, we have that pressure times the volume raised to the n power is equal to C, which is a constant. Then what this process looks like on a PV diagram is the following. So we have our pressure and our volume, and we are going to choose pressure at state 1 is greater than pressure at state 2. And then our volume at state 1 is smaller than our volume at state 2. So here is our state 1. And here is our state 2. All right, and then our process curve will look like this, where we have here that PV raised to the n is a constant. All right, the equation for this process curve is given to us by solving this equation for P in terms of V. So we can find the equation for this process curve. To be P is equal to our constant over V to the n, or C times V to the minus n. Okay. Okay. Also, since PV to the n is a constant, that means that our states 1 and state 2 are related by that constant. Does that make sense? So if we always know that pressure times the volume at any given state raised to the n power is equal to a constant, that means that state 1 and state 2, P times V to the n is the same constant. Okay. All right. One other thing I want to mention is that in the special case where n is equal to 0, we have PV to the 0 is equal to C, which just means that pressure is equal to a constant. So that would be an isobaric process, right? Okay, cool. So now we want to determine the boundary work for a polytropic process of exponent n. So we have our usual equation that the boundary work is equal to the integral from state 1 to state 2 of P dV. All right, and so in order to solve this integral, we need a relationship between P and volume. Or we need pressure as a function of volume. All right, and we know that it's polytropic, so we can say that for a polytropic process, we know that P V to the n is equal to a constant. So we're going to solve this for P, and we have P is equal to C times V to the minus n. And I'm going to take that result and I'm going to plug it into here. Okay, so let's do that. So now we have that WB is equal to the integral from state 1 to state 2 of CV to the minus N dV. All right, so now our integral is in terms of volume, and we can integrate this how we normally would. As a reminder, the integral of x to the a power dx is equal to x over a plus 1 divided by a plus 1. And this is for all a not equal to minus 1. If a is equal to minus 1, does anybody remember what the integral of 1 over x dx is? Natural log, yeah. Sophia, right? Okay, thank you. Okay, so this is our reminder. So what that means is that this integral is equal to the following. We have c times v minus n plus 1 divided by minus n plus 1. Evaluated between volume 1 and volume 2. And this is assuming n is not equal to 1, or minus 1, sorry. Or sorry, n is already negative, so assuming n is not equal to 1. Okay, so if I evaluate this integral, I get that c over 1 minus n is equal to v2 1 minus n minus v1 1 minus n. Okay, so this is our final result for boundary work for this process. And it's also important to note that we have C is equal to PV times N. And we can compute that using either our state 1 or state 2, because they're the same. They'll always give you the same constant. And then another important thing to note, C has units. Right, so we have pressure times the velocity raised to a power. All right, so this has units of pressure times units of volume raised to whatever the n power is. Okay, so knowing this, let's substitute those values back into our equation so that we have our boundary work in terms of pressure and volume at states 1 and 2. So the next thing that we're going to do is we are going to take this expression and we're going to substitute it in here. We're going to substitute C equals P1 V1 to the N, and it's also equal to P2 V2 to the N. I'm going to be a little bit clever about this because I'd like to group things at state 2 and state 1 together. So you'll notice that C is multiplied by volume at state 2 to the 1 minus n, and then it's also multiplied by a volume at state 1 to the 1 minus n. So I'm going to use both of these versions of C, okay, because they're equivalent. So I'm going to write this out in a couple of steps just so it's very abundantly clear what I'm doing here. So I'm going to keep my 1 minus n, 1 over 1 minus n out front, and then I have C times V2 1 minus n minus C times V1, 1 minus N. All right, and so I would like to include this version of C because it relates state 2 here. And then I am going to use this version of C on this term because the last term is in terms of state 1. Does that make sense? They're still the same value of C. They're equivalent. Okay. So I will put those in here. So now we have that 1 over B over 1 minus N is equal to P2 V2 to the N power V2 1 minus N minus, actually, I'm keeping the same thing, but I just want to color code it. So this is P2 V2 to the N, V2 to the 1 minus N. This is exactly what I wrote before. I just changed the color. And then for this C, I'm going to put in P1 V1 to the N times V1 1 minus N. Is that clear for everybody? Okay. Okay. Does anybody remember what we can do when we have like this V2 to the N times V2 to the 1 minus N? Can we combine the exponents? Yeah, we just add them, right? So I'm going to do that next. So I have 1 over 1 minus N still hanging around out front. And then I have P2. And then what is my exponent on V2? It's just 1. How beautiful and simple. And then the same thing for the second term as well. All right, so our final answer is that we have the pressure times the velocity at state 2 minus the pressure times the velocity at state 1 divided by 1 minus N is our expression for the boundary work. And this is for a polytropic process with N not equal to 1. Do you guys have more space on this page, or did you also get to the bottom of the page at this point? You're at the bottom? I'd like a little bit more. I'm sorry. I think I can fit it on mine. So hopefully you also have like a little margin left. So this is the answer for a polytropic process for all N except for N equals 1. So we need to figure out, well, what is it when N equals 1, right? So if N is equal to 1, we have PV is equal to C, which is equal to P1 V1 and P2 V2. And so this all implies that P is equal to C divided by V. So our integral here for our boundary work from state 1 to state 2 of P dV is equal to our integral from state 1 to state 2 of C over V dV, which is just C times the natural log of volume evaluated from state 1 to state 2. So we're going to evaluate our volume from 1 to 2, which gives us C times the quantity of natural log V2 minus natural log V1. Does anybody remember how we can rewrite that expression with the natural log? Yeah, so if we subtract 2 natural logs, it's just like the natural log of those 2 things divided, right? So we have C times the natural log of V2 over V1. All right, so this means that WB is equal to P1 V1 natural log of V2 over V1, or we could also use P2 V2 natural log of V2 over V1. And this is for n equals 1 and a polytropic process. All right, so that last step, just to explain in a little more detail. So we had that our constant can be equal to P1V1, or it could be equal to P2V2. So we can write it both ways, they're equivalent. Does that make sense? Any questions on this? Not too bad? Okay, cool. Okay, so suppose we wanted to model a process as a polytropic process. How would we find what the polytropic exponent n might be? So we're going to assume that we have been given or that we've measured. We have these quantities in some way. We have P1, we have V1, we have P2, and we have V2. All right, so we have pressure and volume at two different states of this process. And so we want to find what n is. So if the process is polytropic, we know that by definition, P times V to the n is equal to a constant. And we also know that this holds for both state 1 and state 2. So we have, that's wrong, P1 times V1 raised to the n is equal to P2 V2 raised to the n. Okay. So what we're going to do is we are going to take our expression P1 V1 to the n is equal to P2 V2 to the n. And I'm going to divide by P2 and divide by V1. So I get my pressures on one side and my volumes on the other. So I have P1 over P2 is equal to V2 raised to the n divided by V1 raised to the n, which is just like the quantity V2 over V1 raised to the n, right? Any ideas on how we can isolate n from this? Yeah, take the natural log. So I'm going to take natural log of P1 over P2 is equal to the natural log of V2 over V1 raised to the n. Oh, not to the 2, to the n. All right. When we take a log of a quantity raised to a power, that power comes out front. So this is equal to n times the natural log of V2 over V1. All right, so I'm just going to solve this for n. So we have that n is equal to natural log of P1 over P2 divided by natural log of V2 over V1. All right, so if you had data for two states for a polytropic process, this is how you would calculate the exponent n. Okay, questions? Okay, let's do an example. Okay, so we have that warm air is contained in a piston cylinder assembly oriented horizontally, which I'm going to draw you a picture right now. So here is our horizontally oriented piston cylinder. There's our piston. And our piston is connected to a spring. Like so. And we have air inside here. All right. The air inside our cylinder is going to cool down slowly from an initial volume of 0.003 cubic meters to a final volume of 0.002 cubic meters. And during this process, the spring exerts a force that varies linearly from an initial value of 900 newtons to a final value of 0. The atmospheric pressure is 100 kPa, and the area of the piston face is 0.018 square meters. We can neglect friction between the piston and the cylinder wall. And for the air, we want to determine the initial and final pressures in kPa and the work in kilojoules. Okay, so does the setup make sense? So we've got warm air in here. And then as that air cools down, our volume is going to shrink and our spring is going to relax as it moves to the left. Okay. Okay, so let's write down what we are given. We are given two states for the volume. So we're given that the initial volume, I'm going to call that V1, is 0.003 cubic meters. And we're given that volume 2 is 0.002 cubic meters. The force of the spring is given to us between states 1 and state 2. So what happens is from volume 1 to volume 2, our force goes from 900 newtons down to 0 in a linear fashion. And then this is linear. Okay. And we're given that this area is 0.018 meters squared. And then I think that's all the givens, right? Yes. And we want to find P1, P2, and WB. All right, so what do we think our system should be? Should be an open or closed system? I feel like I heard someone whisper closed. Is that true? Did someone whisper that? Because that's right. So that's good. So we want to use a closed system. Nothing is leaving our piston cylinder assembly. So we're keeping our mass the same. So we're going to choose a control mass, which is the air inside of our piston cylinder assembly. So this is our closed system. All right, which means that M is equal to constant. We're making a few assumptions, so we should list them. So we are assuming negligible friction. We are assuming the process is slow enough for a quasi-equilibrium. And we're also assuming, this is given to us, that the spring force varies linearly with volume. Okay. So, we already know from looking at boundary work that we need to know the pressures to solve for boundary work, right? So our first step should be figuring out the pressures. Does everybody agree with that strategy? Okay, any ideas on how we might set this up? We know some things about forces. We know about an area of that piston. Do we have any tools at our disposal? So yeah, we want to look at force of the pressure, right? Is pressure times area. So that's a great idea. Thank you, Mark. Um, and the way I'm going to tie all of this together is I'm going to do a free body diagram, and I will use that to find the force of the pressure. Okay. So thank you. Yes, very good. So let's draw a free body diagram for the pressure or for the piston. Okay. Mark already volunteered that we have force from the pressure, which is pressure times the area. I fully agree. What other forces do we have acting on our piston? I don't know if I'm hearing things. Did someone say atmospheric pressure? Was that uttered or am I making it up? No, I mean, it is. So maybe I'm talking to myself in my head over here. So we have we have atmospheric pressure. You hear what you want to hear sometimes, I guess. So we have force of the atmosphere is P atmosphere times A. What else? Yeah, the spring, the spring. So we have F of our spring. I heard gravity suggested. Gravity does act on our piston cylinder, but in this direction. So that's not going to help us to find the pressure because pressure is acting in the horizontal direction. So we're going to do a sum of the forces in X. Does that make sense? Okay, cool. So since we assume quasi-equilibrium, that means that our acceleration is 0. Or we're assuming it to be 0 anyways. So our sum of the forces in the X direction is going to be equal to 0. I like writing this a little differently. So sum of the forces in X is equal to mass times acceleration in the X. And our sum of the forces, we have only one positive X direction force, assuming this is our X coordinate system. So we have P times A minus P atmosphere times A minus F of the spring. And that's equal to 0. And it's equal to 0 because I'm saying AX is equal to 0. Okay. Okay. All right. So we want to find the pressure. So let's solve this expression for the pressure. Oh, I gave us lots of room. Look at that. Okay, great. Okay, so solve for P. The pressure is then equal to F of the spring, so force of the spring divided by A plus P atmosphere. All right, so we have our expression now for pressure, and we want to find P1 and P2. The atmosphere is always the same, whether we're at state 1 or state 2. Area is always the same, whether we're at state 1 or state 2, but the force of our spring changes, right? So now we're going to apply this to state 1 and state 2. And it looks like this. So P1 is going to be force of the spring at state 1 divided by A plus P atmosphere, which is, we have 900 newtons is our initial force on the spring, divided by 0.018 meters squared. So these values were given to us before. We know that 1 Newton per meter squared is a Pascal. And we also know that 1000 pascals is 1 kilopascal. All right, so our pascals cancel out, our newtons cancel out, and our meters cancel out as well. So we're left with units of kPa. And when we multiply this all out, we get 150 kPa. Right? And now we're just going to do the same thing for P2. So P2 is force of the spring at state 2 divided by A plus P atmosphere. What is the force of the spring at state 2? It's 0, right? So we have 0 over 0.018 meters squared. Oh, guys, I forgot the atmosphere on the first one. Sorry, we got to go back. It does work out to be 150, but we also need that P atmosphere is 100 kPa. So this is P atmosphere, and then this is F of the spring over A. All right. Okay, so for P2, we have no force from the spring contributing. We just have P atmosphere. So we just have 100 kPa here. Let me move this up. Okay. So that means that pressure at 2 just must be 100 kPa. All right, so here's our P1, here's our P2. And so now all that's left is to find WB, right? When we do our work calculation, though, we would like to know an expression for the pressure, right? We need to have an equation for the pressure as it really relates to the volume. So we need to know a little bit more than just state one and state 2, right? So let me write that down. When calculating WB, we need a function for P as it relates to volume, right? So what we're essentially going to do is this similar process, but we're going to do it for just a general pressure between states 1 and state 2. So we want to keep the force of the spring in there and figure out how P changes as a function of volume. All right. Okay, so let's start with writing an equation for the force of the spring. Because we know that in general, the pressure is equal to the force of the spring divided by A plus P atmosphere, right? P atmosphere and A are always going to stay the same throughout all of the states. And all we need to do is we need to figure out an equation for this that depends on volume. All right. We already drew a picture of this. Right? So we had from volume 1 to volume 2, we have this linear curve. So this is 900 and this is 0. Here's our force. Right? So if this is an equation of a line, we know that the force of the spring looks like A times the volume plus B, right? So this is our slope. This is our intercept. Is everybody with me so far? Okay, so essentially we have two coordinates on this line, so we can figure out what the slope and the intercept are. We have 2 points of data, 2 unknowns. We can figure this out, right? Okay, so at state 1, we have that F spring at state 1 is 900 newtons, which is equal to A V1 plus B. And at 2, we have that F spring 2 is equal to 0 newtons, which is A V2 plus B. Okay? Any suggestions on how to solve these? This system of equations? I'd suggest we perhaps subtract them from one another and isolate A first. Does that sound okay? Okay, so we're going to subtract. I'm going to call this equation 1, and this is going to be equation 2. So I'm going to do equation 1 minus equation 2 gives us 900 newtons is equal to A times the quantity V1 minus V2. And then we have plus B minus B. So these cancel. Is everybody with me so far? Cool. All right. Fantastic. So this means that A is equal to 900 newtons divided by V1 minus V2, which is 9 times 10 to the 5th newtons per meter cubed. I plugged in the volumes, V1 and V2. We have those, right? Okay, so now we can go to equation 2 or 1, it doesn't matter, and plug in A and solve for B, right? So we're going to plug in A into equation 2 and solve for B. All right, so when we do that, we get that 0 newtons is equal to 9 times 10 to the 5th newtons per meter cubed times V2 plus B, which means that B is equal to minus 1.8 times 10 to the 3 newtons. So we have A, and we also have B. Oops, this is B, and then this is A. Okay, so now we have our equation for our force. So that we have force of the spring is equal to 9 times 10 to the 5 newtons per meter cubed times the volume plus, nope, sorry, minus 1.8 times 10 to the 3 newtons. Little check of the units. I always like to do this when I'm doing these types of calculations to make sure that I didn't mess something up. Our coefficients on A have newtons per meter cubed. That makes sense because we're multiplying that by volume, which has meters cubed. So we end up with newtons after we do that. And then our second term is also in newtons. So we expect both terms to have newtons so they can add together, and then we want them to be a force. So that looks good. Okay. Okay, so this means that we can plug this in to our expression for pressure, this guy. So we have that pressure is equal to the force of our spring, which is 9 times 10 to the 5th newtons per meter cubed times volume minus 1.8 times 10 to the 3 newtons divided by area plus P atmosphere. Right? So this means that pressure varies linearly with volume. I should have added another page. Are you guys really hosed without the extra page? You're in a bad way? You're okay? Okay, I'm gonna add a page here. I'm sorry. I try not to do this, but it happens sometimes. Okay. So now we can solve for the boundary work. We are now ready to solve for WB. Okay, so WB is the integral from state 1 to state 2 of pressure times dV, which is the integral from V1 to V2 times our equation. So we have 9 times 10 to the 5th newtons per meter cubed times volume minus 1.8 times 10 to the 3 newtons divided by our area plus P atmosphere. That whole quantity is integrated over dV. Okay. All right, so let's integrate this. I have essentially 3 terms here. The first term, the 9 times 10 to the 5th times V over A. A is still a constant, right? So that's just a constant times volume. And then our second term, minus 1.8 times 10 to the 3 newtons over area. And our third term, atmospheric pressure. Those are both constants with respect to volume. So this isn't too bad to integrate, all right? So what we get is we have 9 times 10 to the 5th newtons per meter cubed times our, or sorry, divided by A. And then what do we get when we integrate volume? V dV. V squared over 2, right? Okay. V squared over 2. And then we have minus 1.8 times 10 to the 3 newtons divided by A. dV just integrates to V. And then we have plus P atmosphere times V. And we're going to evaluate both of these, or all of these terms between V1 and V2. Okay. And when we do that, we get minus 0.125 kilojoules. Does anyone remember what a negative work means in our sign convention? So output is always positive. If we have positive work, we're getting work from so this means it's input. I always remember the sign convention as like, as an engineer, ideally we want to get work out of a system. So that's yay, positive work, right? And then if it's negative, it's less of a good thing that we have to input power into the system. That's not always the case, but it helps me remember. Okay. So this minus sign means that work was input. All right. So this is our answer. And just to note, we could have also done this by finding the area under the curve. Let me do this over here. So alternately, we could have found WB by computing the area under the PV curve, which looks like this. So we have our pressure and our volume axes. This is V2, this is V1. And then we have pressure 1 and pressure 2. And we found out when we solved this equation here, we knew that pressure is linear with volume. So we have that this is a line. And then our area under this curve is just this. All right, so if you wanted to, you could, do the area of this rectangle and then add the area of the triangle on top. Personally, if I've already gone through the trouble of finding this expression to prove that the pressure is related to the volume in a linear fashion, I would just integrate myself, but either way is correct. Okay. And you get the same answer. Do you want to see the same answer? No? Okay. Okay. Let's take a break. Okay. Let's dive back in. So now we're going to talk about conservation of energy, which is also called first law of thermodynamics for a closed system. So if you remember, our conservation of energy principle that we already talked about earlier in this unit says that the net change in total energy for the system is equal to the energy added to the system minus the energy removed from the system. So we're just saying all the energy has to be accounted for. Okay, so if we have a process that goes between state 1 and state 2, the conservation of energy for a closed system can be written as the following. So we have energy at state 2 minus energy at state 1 is equal to the energy in minus the energy out. And we can rewrite this as the heat in, Q in, plus the work in minus the heat out and the work out. All right, and just note that this E1 and E2 is the total energy, where our total energy is broken down into internal energy, kinetic energy, and potential energy all summed together. So this is internal energy, kinetic energy, and then potential energy. which we can write as U plus 1/2 mv squared. V here is the velocity, of course, plus mgz. Or we can rewrite this whole thing with mass on the outside multiplied by all the specific versions of these things. So if we pull mass out, then we have the quantity U. So lowercase u is the specific internal energy. Plus 1/2 velocity squared plus g times z is equal to, oh, and then this is also equal to, we can have mass times the specific energy, specific total energy. Okay. So this means that for our closed system, we then have our internal energy plus our kinetic energy plus our potential energy, all evaluated at state 2, minus our internal energy plus our kinetic energy plus our potential energy evaluated at state 1 is equal to Qn plus Wn minus Q out plus W out. And then we did this before, but we can rearrange this as Q in minus Q out. Oh, that's a W. Minus Q out plus W in minus W out. All right, where Q in minus Q out is how we write Q net. And W in minus W out is how we write minus W net. Okay. Okay. So that means we can rewrite our equation in terms of net heat transfer and net work out. Our net heat input is Q net, which I already just wrote is Q in minus Q out. And then our net work output is W net, sometimes just called W, is equal to W out minus W in. Okay. I haven't really said anything new just yet. This is all what we've talked about before. So if we use this, then we have conservation of energy then becomes E2 minus E1 is equal to Q minus W. Or if I expand this out, I have mass times my specific internal energy plus 1/2 V2 squared plus GZ2 minus our mass times our internal energy at 1 plus 1/2 V1 squared plus GZ1 is equal to Q minus W, where Q and W are these quantities here. Does that make sense? Okay. The conservation of energy equation for a closed system can also be written in differential form. So we have a differential change in energy and total energy is equal to delta Q minus delta W. Or it can also be written in rate form, so per unit time. So this first term here, the time rate of change in total energy in the system, we would write as dE dt. And this is just E dot in minus E dot out. And then we have the rate of energy added to the system minus the rate of energy removed from the system. Okay, so this right-hand side then is equal to Q dot in plus W dot in. So the dots over the letters still mean a derivative with respect to time. And then we have minus Q dot out plus W dot out. And as a reminder, this is for a closed system. Okay. We can write this as well in terms of net rates of heat transfer and work, just like we did for before we added the rate element into this. So our net rate of heat input is Q dot net is equal to Q dot, which is Q dot in minus Q dot out. And our net rate of work output is W dot net, which is W times W dot out minus W dot in. All right. So this means that dE dt is equal to Q dot minus, oh, there's a dot here, minus W dot. Again, for a closed system. And here, E is the same definition that we've talked about a bunch of times. So we have internal energy plus 1/2 mv squared plus mgz. All right. If we have a process that does not change with time, then that means it is a steady process. All right. So no changes in time means if we take the time rate of change of the total energy, it is 0. That also means that since dE dt is E dot in minus E dot out, and that's equal to 0, then that implies that the rate of energy in equals the rate of energy out. All right, so for a steady process and a closed system, we have that Q dot in plus W dot in is equal to Q dot out plus W dot out. Make sense? All right, cool. So in order to be able to apply the conservation of energy principle in a meaningful way, We're going to need a way to relate internal energy to other properties. So that term U. And that's what we're going to do in our next topic. That's chapter 4 in the book. Um, so we will get to that on Tuesday. But a property that often appears in the conservation of energy equation is called enthalpy. And this is defined by the variable H. And H is equal to the internal energy plus pressure times volume. Or it can also be, let me write this on this side. So H, enthalpy, total enthalpy can also be written as mass times the specific enthalpy. Which is equal to M times the specific internal energy times P times the specific volume. Oh, there's an M in there. M, P, V. So there's M in all of those terms in that equation. So this can be written without the mass. So we have enthalpy, specific enthalpy is equal to specific internal energy plus P times specific volume. And at least in my experience, this is the most common form of this equation that you'll see. But if the variables are capitals, it just means it's total. So the mass is in there. Okay. Okay, cool. So let's do an example. All right, so we have 1.2 pounds of mass of steam in a piston cylinder assembly undergoes a polytropic process with n equals 2 from an initial state where the pressure is 500 psi. The specific volume is 1.701 cubic feet per pound of mass, and the internal energy is 1,363.3 BTUs per pound of mass. To a final state where the specific volume is now 3.802 cubic feet per pound of mass, and the internal energy is 990.58 BTUs per pound of mass. During this process, an electric switch is turned on and a 110-volt source supplies electrical power input to a resistance heater inside the cylinder at a constant rate of 40 BTUs per hour for 30 minutes. Neglecting the changes in kinetic and potential energy, determine the boundary work and the heat transfer for this process in BTU. So we have a lot going on here. It was a lot of words, a lot of numbers, a lot of things. I suggest always starting a problem with drawing a picture if you're not given one, along with writing down with appropriate symbols all the information that's given to you. So let's start there. So we have a cylinder and a piston assembly. Generally, if it's not told to you that it's a horizontally oriented piston, they go this way. All right. And we have a heating element in here, which I will draw like this. And then this cylinder is filled with steam. So we have water in here, essentially. And let's see what we're given. So we're given, our mass is 1.2 pounds of mass. We are given that it is a polytropic process. With n, oh boy, with n equals 2. We're given a lot of information about state 1 and state 2, so I'm going to organize it that way. So we have state 1 and state 2. So for state one, we're given the initial pressure. Is 500. Actually, am I going out of order? No, it's not. Okay, that's the first thing. So this is pounds per square inch. We're also given the initial specific volume is 1.701 cubic feet per pound of mass. And we're given our internal energy is 1363.3 BTU per pound of mass. All right, and then for our second state, we're not given the pressure, but we are given the specific volume, which is somewhere in here, 3.802 cubic feet per pound of mass. And the internal energy at state two is 990.58 BTU per pound of mass. We're also given that there is electrical work input. So we have and that is as a rate. So we have rate of electrical work input, W dot E, is 40 BTU per hour. And this is supplied over a time of 30 minutes or 0.5 hours. And we're going to neglect kinetic energy and potential energy. Oof. All right, so we want to find a couple of things. We want to find boundary work, WB, and we want to find Q. Right? So the problem setup makes sense to everybody and how we've kind of synthesized all of this information that was given to us. Okay. All right. So first, let's determine our system. What kind of a system should we use here? I'm not going to interpret what I heard. It was just like, what was that? Anybody? Yeah, it's still a closed system. So we're gonna define our system as essentially the steam inside of this piston cylinder apparatus. So this is our closed system. This is a closed system, which means that M is a constant. Okay. Is this an expansion or compression process? I heard expansion. Yeah. Yeah, great. You guys are quicker than I can write, but that's good. So why do we think it's expansion? Right. So our second volume is larger than our first volume. All right, we can just compare our specific volumes in this case because the mass is constant, but if not, if the mass wasn't constant, we'd want to be careful about just comparing specific volumes, right? Okay, fantastic. All right, so let's talk about boundary work. So we know that our equation for boundary work is the integral from state one to state two. So from volume 1 to volume 2, since we're integrating with respect to volume, and we have pressure times dV. We need an expression for P as a function of volume, as always. But we're given that it's a polytropic process with n equals 2. All right, so that means that we can already write that P times V2 is a constant, which is equal to P1 V1 squared, or P2 V2 squared. So we have that this expression for pressure in terms of volume is just a constant divided by velocity squared, or C times V to the minus 2. All right, so this is just our polytropic process with n equals 2. Right? So we can do this integral now. So we have WB is equal to the integral from volume at state 1 to volume at state 2 of C times V raised to the minus 2 dV. And what does this integral look like? Yeah, so we have minus 1 over the volume, and we're going to evaluate that from V1 to V2. So we have minus C over V2 minus a minus C over V1, which is C times the quantity of 1 over V1 minus 1 over V2. So I just factored out a C and tidied up the minus signs in there. Okay. All right. I'm also going to use, I can use either one, they're equivalent. Does anybody have a preference on whether we substitute P1 V1 squared or P2 V2 squared for the coefficient C? Is one more strategic than the other, perhaps? We don't have P2, right? So I would prefer to use P1 V1 because we have both of those things, right? All right, so let's do that. So I'm going to use this expression to substitute in for C. So I have P1 V1 squared times the quantity of 1 over V1 minus 1 over V2. All right, and we have all of these things. So now we can use this to find the boundary work, right? So we have P1, we have V1, and then we also have V2. We have V1 and V2 in kind of a roundabout way because we have the specific volumes. So we have to sort that out. I'm going to do that right here. So we have V1 is equal to mass times the specific volume at 1, which is 1.2 pounds of mass times 1.701 cubic feet per pound of mass, which is 2.041 cubic feet. And then in a similar fashion, we have V2. So we have mass times specific volume at 2. So we keep our same 1.2 pounds of mass. And our specific volume is now 3.802 cubic feet per pound of mass, which gives us 4.562 cubic feet. Okay. So plugging all of this in, I'm going to do it on the next page just because I don't want to, I want to keep it legible. Okay, so our P1 is 500 PSI and our V2 is 2.041 feet cubed, and we're going to square that times 1 over V2, which is 4 point, no, sorry, 1 over V1, which is 2.041 feet cubed minus 1 over 4.562 feet cubed. And now we need to do some conversions. So 1 BTU is 778.17 feet times pounds of force. And 1 PSI is 1 pound of force per square inch. And then I have one small little conversion. I'm just going to shrink this a teeny weeny bit. Okay. And then our last conversion is that 12 inches are in a foot squared. Okay. So let's work out the units here. So we have square inches cancel with square inches. We have, so we have, this is a little bit clunky, but right here we have feet to the 6th, right? And then here we have feet, this is feet cubed times another feet times feet squared. So we have feet to the 6th again. So I'm going to cancel these out. So these are all the feet. The feet all cancel. Does everybody see that? Okay, cool. And then PSI balances with PSI. Pounds of force balance with pounds of force. And then we're left with BTU. So we have WB is equal to 104.4 BTU. This is greater than 0, right? So what does that mean about the work? Is it done on the system or by the system? Yeah, work is done by the system. Very good. And if you remember, this is an expansion process. Expansion. So that makes sense, right? Logically, that work would be done by the system on the surroundings. Okay, now we want to determine our heat transfer. We want to find Q. All right, so our conservation of energy equation is E2 minus E1 is equal to Q minus W. All right. So I'm going to expand out the total energy in terms of internal kinetic and potential energies, just like how we've done before. So I'm going to pull out the mass. So I have specific internal energy plus 1/2 V squared of state 2 plus GZ at state 2. So this is our total energy at state 2 minus our total energy at state 1. So we have our internal energy, our kinetic energy, and our potential energy is equal to Q minus W. We're neglecting potential and kinetic energy, right? So I can get rid of those terms. So this is my kinetic energy, and this is my potential energy. So neglect, PE, neglect, KE. All right. And I'm going to rewrite this because now it's a whole lot simpler. So I have my mass times internal energy at state 2 minus internal energy at state 1. And this is equal to Q minus W. Okay, we want to find Q, right? And we already know the mass and we're given the internal energy at states 1 and 2. So we just need to put in the net work term, right? What works do we have to consider for this problem? Yes, excellent. So we have our boundary work and our electrical work that we want to take care of. So our net work output is W, which is going to be the WB boundary work plus our WE, the electrical. Sign is wrong, right? Our electrical work is an input work, so we give it a minus sign. Our boundary work, we already figured out, is an output work, so we keep that positive. Does that make sense for the signs? So this is W out, and this is W in. Everybody feel good about that? Okay. All right, so we already know WB. So let's sort out WE. So W dot E is a constant. We don't want W dot though, we want just W. So we're gonna have to integrate this over time to get rid of the dot. So we're gonna use the following. So we have WE is equal to the integral from T1 to T2 of WE dot dt. WE is just a constant, so this integral is just W dot E times T2 minus T1, or W dot E times delta T. And we were given both W dot E and delta T, right? So plugging in what we were given, we have that WE is 40 BTU per hour times our delta T was 30 minutes, which is half an hour. So we have 20 BTUs, right? So now we're just going to solve for heat transfer. So we have Q is equal to M U2 minus U1 plus W B minus WE. Okay. So plugging in the values that we have, so we have 1.2 pounds of mass times 990.58 minus 1363.3, bless you, BTU per pound of mass. So our pounds of mass are going to cancel here and we have just BTUs, which is convenient because our next term is our boundary work, which we have in terms of BTUs, which is 104.4 BTU, minus our electrical work is 20 BTU. Which gives us Q is minus 362.9 BTU, which is less than 0. So what does that mean about the direction of where the heat's going? Is the system gaining or losing heat? Losing heat. Did that example feel okay for everybody? Any questions on it? All right. Well, that is all I have for you. Right on time. Look at that. Okay, fantastic. So next week we'll start our next topic, which is about figuring out internal energy based on properties.